Welcome back to the channel. In our second video on Math Review for a Physics 1 course, that's the playlist here, we're going to talk about scalars, vectors, and a little bit about vector addition. So first, we're simply going to talk about scalars, essentially just a number without direction, vectors, which have direction, parallel and perpendicular vectors, as well as a few other considerations, anti-parallel, and maybe in between some of these things, and finally, how to add vectors graphically. This is a very important, hopefully review, but very important video for understanding and succeeding in your physics course. Let's get into it. Let's talk about what a scalar is. And it is actually something very simple that you already pretty much know what it is, even if you don't think you do. But it's just a number. So let's say I have 3 cats. Well, it's a scalar. The scalar specifically is the number 3, and cats are the units. Because I could have 3 apples, 3 dogs, 3 fish, anything like that. Another thing is 14 days. This is another scalar. So it is a very simple concept. It's just you need to know this to understand the difference between a scalar and a vector. So, real quick here, scalars have magnitude. No direction, just a magnitude. It doesn't make sense to say 3 cats north. If you're talking about the location of the cats, well, now that's different. The 3 cats are located 6 miles north. That's a location which is different from describing the cats. So it sounds very silly and simple, but that's because it is. And you need to know this because you need to know what a vector is. So last thing here we're going to talk about is there's time, mass, distance, speed, energy. These are all scalars. They do not have a direction. And again, it might seem silly, but you've got to know if something has a direction or not, because then you got to do some special stuff to it. It's not, you don't treat scalars the same as you do vectors. So let's now talk about vectors. This is something that has both magnitude and direction. So before we talked about magnitude, and that's the number 3, 14, a million. Those are all magnitudes. But it has, let me make this super clear, magnitude and now direction. That's what makes it different than, say, a scalar, like 10 seconds. We have to say, I have a position of 3 miles to the east. 3 miles east. We have 3 things going on here. Well, we've got a magnitude, that's the length or length or magnitude of the vector. 3, that's how much. Which direction? I don't know, east. That's what it says. There it is. There's a direction. And again, we always have units. Miles are the units. We could say 3 inches east. It has 3 as the magnitude, east again as the direction, but now it's different units. So in general, scalars and vectors both have units, especially in physics, chemistry, things like that. But something always has a number, a magnitude, but vectors are special because they have direction. And you really want to make these different in your mind. So velocity is not speed, but of course we're going to get into that much in a few more videos. We talk about kinematics. But velocity, acceleration, force, momentum. You're going to learn about all these things in this class. And these are all vectors, which means we need to treat them special. So let's talk about something very basic. And we now know that vectors have a direction. North, left, positive y-axis. These are all directions. And scalars don't have that. But what if we have 2 vectors? I've got one, A, we'll call it. By the way, this is vector notation. I draw it with an arrow and a letter with a little kind of half arrow over it to denote that it is a vector, meaning it has direction. We call this part the head and this part the tail of the vector. Okay? But let's say I have one here. It's just kind of living in space, not doing much. But then there's another vector, B, in the exact same direction. And let's say B is not even the same length or same magnitude as A, but it does have the same direction. We say that these are parallel vectors. Similarly, if I got 2 new vectors, one that points straight up and one to the right, and forms a right angle between them, vector D down here and vector C up here, these are perpendicular. It's very important to be able to kind of understand this basic idea, but also recognize it in a problem. So you'll see a lot of things with vectors, and there's a lot of things we can do with them. And notice that I could move vector B around. I can move it, I don't care, over here. It doesn't even matter down there. There's still parallel vectors, because you can always move a vector and essentially have them overlap to really understand the properties of them. Okay? So, basic idea, but you do need to have some comfortability with this. So let me talk about one more thing. And so if I have A pointing to the right, we already said, hey, if B is that way, same direction, they are parallel. But what if B is in the opposite direction? Remember, I don't care about the length, so let's say B is that way. Well, now we call this anti-parallel. And that's really the three things you need to know, though parallel and perpendicular are the key components. Anti-parallel is just, well, the opposite of parallel. You could say that they have a 180-degree angle between them. And I also want to say this angle is 90 degrees. We kind of already said that. This angle is 0 degrees. But then this angle would be 180 degrees. Okay? So, or radians. This would be pi radians. Make sure you understand all that. Those are the special cases. But if we have two more vectors, let's call it C like this and D to the right, and there's some angle of, I don't know, that looks about 45 degrees. Well, this is not perpendicular, not parallel, nor anti-parallel. This is some other. It's 45 degrees. And so we're going to learn how to deal with each of these vectors in relation to the angle between them, as well as angles relative to the positive x-axis. As in, if I have the x and y axis, I can always kind of just move my vector A, let's say, right here. So, well, there you go. I didn't draw it very perfectly, but that's a 0-degree angle. The vector C has a 45-degree angle. And we can deal with vectors in this way as well. The last thing I want to talk about is how to add vectors graphically. We haven't used any math really to describe the vectors. We'll do that in the next video. But here we just kind of want to qualitatively see what the sum of two vectors is. So let's draw what we had before, vector C and vector D to the right. And we said, oh, there's a 45-degree angle between them. That's fine. But now, what is the sum C plus D? That's what we want to kind of ask ourselves. Because just like you can add scalars, 10 plus 20, well, 10 is the scalar. 20 is also a scalar. You know how to add 10 and 20. We can add vectors in much the same way. But remember, we have a direction now, so we have to take that into account. It's not just the magnitude we have to add anymore. We are adding the direction. I'm going to write this down because this is very important, that vectors have a magnitude like a scalar, like the number 5 is a scalar, magnitude, and direction to the left along the x-axis. Those are directions. 30 degrees northwest from my house. That's also a direction. It just depends on what you're doing. We're going to get into that in the next video, how to actually describe it mathematically in physics, but you need to be comfortable with the idea. So, we can add the magnitudes. That's fine. We know how to do that. We learned that when we were 5 years old, essentially, how to add numbers together. But what about direction? And there's a very special way to do this. We essentially form a parallelogram. So imagine taking D, picking it up, well, leaving it where it is, but drawing a new vector D, but just kind of moving it right there. Well, you can see now, hey, this is kind of a parallelogram. So let me make that a dashed line to let you know that we kind of just move this up here. Let me try to do it as accurate as possible. So there's D. Remember, we can move vectors wherever we want. And guess what? C is also kind of here. We could move C in much the same way so that I have kind of a parallelogram. You should have a perfect parallelogram, but since I'm drawing it by hand. And then guess what? C plus D, well, it starts where the two meet, where the two tails meet, and then it ends over here at the opposite end of the parallelogram where the two heads meet. And so I would draw a vector from here to here, try to draw a straight line. This is the vector C plus D. You could call it whatever you want. We can call it R. Sometimes we call it a resultant vector. When we add two things, we have a result. And you can use R for the resultant, or you could have E or call it whatever you want. But just know, hey, I added these two things together. I have to take into account the direction. And so the process, let's say I have some vector A and some vector B straight down. The process is we want to redraw them so that they are together, as in place the tails together. So we'll do that, redraw it. If I'm doing it as if you had a piece of paper. Then think about where the parallelogram might be. Well, I know that there's some vector B here, maybe a little longer. Notice this is not a perfectly accurate thing, but this is the process, and it doesn't have to be perfectly accurate. You want to know the general direction of the sum of these things, A plus B. Okay? It's always going to be between the acute angle that forms them. So let me do it again. In fact, I'll start a new page, and let's try this vector. Call it F1. We'll get used to some subscripts here. F1. And then how about over here? F2. Well, I don't need to actually draw I don't need to be perfect in my diagram. I just want a general idea of where it is, and it looks like it's about there. That's where the sum of those vectors, F1 plus F2, lies. And this is really useful when you're solving problems. You don't need to really ever draw diagrams and do it perfectly, but you want to know the general direction to make sure your answer makes sense. So please spend a little bit of time on that. I will try to put some worksheets, a link to the description for worksheets on my website, betterthanab.com, and you can do a little bit of practice to get used to the idea of a vector and how they're used.